Imagine materials so incredibly tiny, they're practically invisible, but they're shaking things up everywhere, from energy generation to medicine, even cleaning up pollution. We're diving into the really fascinating world of colloidal metal oxide nanoparticles today. Sounds pretty futuristic,
It
correct?
really does, but it's very much happening now. What's amazing is how these, well, nanoscale structures are turning out to be such game changers in fields that seem, totally unrelated sometimes.
Exactly. So for this deep dive, we've looked at a whole load of scientific research papers exploring how these things are made, what they do, their properties. Think of this as your quick guide, your shortcut to understanding the basics and the huge potential of these tiny building blocks.
Yeah, the goal is really to pull out the core ideas, maybe some surprising applications, without getting totally lost in the super technical weeds.
Right. We want you to get a solid foundation.
And just appreciate how fundamental this is. These aren't just niche materials, they're becoming core components that scientists can tweak with, well, remarkable precision now.
Okay, let's unpack that. First things first, the word colloid. Sounds a bit sciencey. What does it actually mean in simple terms?
Oh, it's not that complicated, really. You actually run into colloids all the time, like whipped cream. That's just gas bubble spread through a liquid.
Okay.
Or clouds, tiny water droplets hanging in the air. Smoke is solid bits in a gas. Even milk is a colloid. You've got tiny fat globules floating in water.
Okay, I get it. So it's basically one thing finely mixed or dispersed within another thing. And these metal oxide nanoparticles fit into that.
Exactly. We're talking about solid nanoparticles. Tiny bits of metal oxygen compounds spread throughout a liquid, usually, though sometimes it could be a solid or gas, too.
Yeah.
The key thing, though, is the size, generally between, say, 1 and 1,000 nanometers. It's this tiny scale that makes them behave differently, have unique properties compared to the bulk material.
Right, the size-dependent properties. So how on earth do you make something that small and, uniformly small?
Yeah.
Sounds incredibly difficult.
Well, there are quite a few clever ways, actually. The research highlights several main routes. You've got things like wet chemistry methods, often involving modifying the surface.
Okay.
Thermal decomposition, which is basically using heat to break down precursors and form the nanoparticles. Gas phase methods, using plasma.
Plasma, like in a sci-fi movie.
Sort of.
Oh,
Very
great.
controlled version, yeah. Using ionized gas. And then there's one called nanosecond pulsed laser ablation. Sounds very high-tech.
Okay, pulsed laser ablation. Let's zoom in on that one. What's actually going on there?
It's pretty cool, actually. You take a target material, stick it in a liquid, and then zap it with really short, intense laser pulses.
Zap it.
Yeah, it basically vaporizes a tiny amount of the material. This vapor then cools down really quickly in the liquid and condenses into nanoparticles. And what's really neat is that you can control the size of the nanoparticles and how spread out the sizes are by tweaking the laser things like the power, the wavelength, how long the pulse lasts. And also by changing the liquid or the target material itself.
So it's like using light as a tiny chisel, a nanoscale sculptor.
That's a pretty good way to think about it, yeah. The papers even mention using this to make hafnium oxide nanoparticles with other elements mixed in doped nanoparticles that actually emit light. They have luminescence properties.
Wow.
But, lasers aside, a really common and important approach is aqueous synthesis, just making them in water.
Water. That sounds simpler. And probably greener, too.
Definitely. Water's great. It's stable, cheap, safe, environmentally friendly, like the research points out. The basic idea is you start with metal ions dissolved in the water. They form precursors.
Precursors, like the starting ingredients.
Exactly. And when the concentration gets high enough, supersaturated, they start to clump together, condense, and grow into these nanoparticles.
Okay. And I saw sol gel processing mentioned quite a bit. That sounds a bit more complex than just mixing in water.
It is a bit more involved, yeah. Sol gel is super popular, though, because it gives you a lot of control over the final particle shape and size. It involves some specific chemistry, hydroxylation, and condensation steps using molecular precursors. Water's still really important here. Think of it like building a sort of jelly-like network. The gel and the nanoparticles form within that structure.
A gel network.
Yeah.
Interesting. So lasers, water, gels. What other tricks are in the synthesis toolkit?
Well, there's hydrothermal and solvothermal synthesis. Basically, you react your ingredients in a sealed container at high temperature and pressure.
Sounds intense.
It can be. But the payoff is you often get really nice, well-defined crystal structures, sometimes at lower temperatures than you might need otherwise. If you use water, it's hydrothermal. Other solvents, it's solvothermal. Then you have microemulsion methods. Picture tiny, tiny droplets of water trapped inside oil or the other way around, stabilized by surfactants.
Surfactants, like soap molecules.
Kind of, yeah. Molecules that like both water and oil. These tiny droplets act like miniature reactors, controlling where the nanoparticles form and stopping them from all clumping together.
Like little individual reaction bubbles. Okay, what about sound? I think I read something about sonochemical synthesis.
You did. Sonochemistry uses ultrasound high-frequency sound waves. It creates these tiny bubbles in the liquid, which then collapse really violently.
Collapse.
Yeah, cavitation. It creates these tiny hotspots with extreme temperatures and pressures, which can drive chemical reactions, including nanoparticle formation. The sources give an example of making spherical iron oxide nanoparticles this way. And you could even tune the particle size by changing the temperature or the ultrasound power. It's kind of amazing using sound to build things so small.
That really is wild.
Yeah.
Okay, one more. Seeded growth. Sounds like planting tiny seeds.
That's exactly the idea. You start with some nanoparticles, you've already made the seeds, and then you add more precursor material. This new material deposits onto the existing seeds, making them grow bigger. It's a really good way to make more complicated structures, like core shell particles, where you have one material as the core and then grow a layer of another material around it.
Right. So, okay, we've got this whole arsenal of ways to make nanoparticles, but you make them, and then what stops them just immediately glomming together into one big useless lump?
Ah, yes, stability. That is absolutely crucial. It all comes down to a balance of forces between the particles. There are attractive forces pulling them together, van der Waals forces mostly.
Okay.
And then there are repulsive forces pushing them apart. Often, this repulsion is electrostatic. It comes from charges on the surface of the nanoparticles, the pH of the liquid, the amount of salt or ions in it. These things strongly affect the surface charge and therefore the repulsion. If the repulsion isn't strong enough to beat the attraction, they aggregate, clump up.
So it's like tiny magnets, some attracting, some repelling.
In a way, yes. The surface charge creates this kind of electrical shield around each particle, an electrical double layer. When these shields overlap, they push apart. There's actually a theory, DLVO theory, that helps describe this balance mathematically.
DLVO. Okay. And surfactants popped up again here. How do they help with stability?
Right. Surfactants play a big role. They basically coat the nanoparticles. They absorb onto the surface. This does a couple of things. It lowers the energy difference, the interfacial energy between the particle and the liquid. The Gibbs adsorption equation describes that. And they can also provide a physical barrier, like little bumper jackets, or modify the surface charge to boost that repulsion we talked about.
Nanoscale bodyguards preventing pileups. Love it.
Mm-hmm.
Is it just about the chemistry, or does how you mix them matter too?
Oh, definitely. How you handle them physically matters. For instance, using things like micromixers or designing reactors for smooth laminar flow can help stability by reducing turbulence. Too much agitation can make particles collide more often and stick together.
So gentle mixing can be better.
Sometimes, yes. Although, interestingly, some reactor designs, like helical ones, create little whirlpools called Dean vortices intentionally to promote mixing, which might be useful in some synthesis steps, but could also cause aggregation later. It's a balance.
And what was that Oswald ripening thing? Sounds like cheese aging or something.
Haha. It's a similar idea in that things change over time. With nanoparticles, Ostwald ripening is where smaller particles tend to dissolve, and that material then redeposits onto the larger particles.
Why does that happen?
Because larger particles are actually slightly more stable, thermodynamically speaking. So over time, the small ones disappear and you end up with fewer, bigger particles. This can change the properties and stability of the whole colloid.
Okay, makes sense. So we can make them, we can stabilize them?
Hopefully.
Okay.
But how do scientists actually know what they've got? How do they study things this tiny? Right, characterization. It's absolutely vital. There's a whole suite of techniques. Electron microscopy is huge. TEM, HRM. These let you basically see the nanoparticles, look at their shape, their structure, measure their size directly. Super powerful microscopes for the nanoscale.
Like getting an actual picture.
Exactly. Then you've got loads of spectroscopy methods. UV tells you how they interact with light, their optical properties. FTIR and Raman spectroscopy give you chemical information, what bonds are present. XPS is really useful for looking at the surface chemistry and the electronic states of the elements right at the surface. Crucial for understanding how they'll interact with things.
Okay.
Photoluminescence tells you if and how they emit light. And there are specialized techniques, too, like ATR attenuated total reflectance, specifically for probing surfaces.
Wow, it's like a full diagnostic toolkit. What about the internal structure? Like, are they perfectly ordered crystals or just jumbled atoms?
Good question. That's where X-ray diffraction, XRD, comes in. By bouncing X-rays off the particles, you can figure out their crystal structure, how the atoms are arranged inside. People even do in situ synchrotron XRD, watching the structure form or change during a reaction, which is pretty amazing.
Real-time analysis?
Yeah. And electron diffraction, ED, often done in the electron microscope, can also identify crystal structures, especially for very small crystals.
Right.
Lastly, UV-DRS, diffuse reflectance spectroscopy, helps estimate the band gap.
Band gap.
It's a key electronic property, basically tells you the minimum energy needed to get electrons excited by light. Really important for applications like solar cells or photocatalysis.
Right. It's amazing how many angles they can probe something so small from. Okay, now the really exciting bit. What are people actually doing with all these nanoparticles? You mentioned so many fields earlier.
Oh, the applications are incredibly broad, and new ones keep emerging. Let's start with energy. In solar cells, people are using colloidal metal oxides to try and improve how well they absorb sunlight and convert it to electricity. For LEDs and photodetectors, some metal oxides are transparent but also conductive, which is useful for electrodes. And they're being used to make better light sensors. By controlling the nanoparticle size, you can even tune the color of light emitted by LEDs.
So making our gadgets potentially more efficient, maybe more sensitive.
That's the idea. They're also showing up in supercapacitors, energy storage devices as electrode materials. And there's interest in using them for thermoelectric devices, converting heat to electricity, or vice versa. Catalysis is another massive area. These nanoparticles have a huge surface area for their size, which makes them great catalysts for speeding up chemical reactions.
Like what kind of reactions?
All sorts.
Yeah.
Important industrial ones, like converting CO or CO2 into methanol, or reactions used in making pharmaceuticals, like Suzuki-Miura cross-coupling. Having catalysts as nanoparticles means you use less precious metal and you can control things very precisely.
Speeding up chemistry with tiny, tailored particles? That must be huge for industry and maybe even green chemistry.
Absolutely. And it applies to fuel cells, too. They're being tested as electrocatalysts in things like DBFCs and DMFCs, trying to make those electricity-generating reactions more efficient.
Okay, that's energy. What about the environmental side? How are they helping clean things up?
This is a really promising area. Wastewater treatment is a big one. Different metal oxide nanoparticles, tin oxide, iron nanoparticles, magnesium oxide are being used to break down nasty pollutants like dyes from textile factories or pesticides.
Break them down. How?
Through chemical reactions, often photocatalysis, where light helps activate the nanoparticle. They can also absorb heavy metals, arsenic, lead, mercury, chromium, basically stick them to their surface to remove them from water, even radioactive stuff. People are also combining them with other materials like carbon nanotubes or these spongy materials called aerogels to make even better filters or reactors.
So tiny cleanup crews for water and soil.
Pretty much. The sources mention specific examples like specially modified iron oxide nanoparticles for pulling uranium out of water, or composites with silver for disinfection.
That's fantastic. Okay, what about biology and medicine? That sounded really cutting edge.
It really is. Magnetic nanoparticles are a hot topic here.
Mm.
Because they're magnetic, you can potentially guide them to specific spots in the body using external magnets.
For what?
For targeted drug delivery, for instance. Load the nanoparticle with a drug, guide it straight to a tumor, and release the drug there, hopefully reducing side effects.
Wow.
They're also used in magnetic hyperthermia. Get the magnetic nanoparticles into a tumor, then apply an alternating magnetic field from outside the body. The nanoparticles heat up and cook the cancer cells.
That's heat. That's amazing.
It is. And they're used as contrast agents in MRI scans, making images clearer. Researchers are building really sophisticated systems, like combining nanoparticles with liposomes or making these nanorods coated in silica that carry chemo drugs.
So complex.
Yeah. And beyond cancer, they're used in biosensors to detect specific molecules. And some, like zinc oxide nanoparticles, have antibacterial properties too. It's kind of mind-blowing, the potential impact on health.
Absolutely incredible. Targeted therapies, diagnostics. Okay, briefly, what about electronics?
Yep, making waves there too. Colloidal metal oxides are being used to make thin film transistors, TFTs, which are crucial for displays, especially flexible ones. High performance, maybe foldable screens someday?
Cool.
They can function as charge-trapping layers in flash memory, potentially useful in magnetic data storage, and even smart windows.
Smart windows.
Yeah, coatings for windows that can change their transparency or how much heat they let through electronically could save a lot on heating and cooling.
That sounds like something I want. Okay, you also mentioned something called heterostructured nanocrystals earlier. HNCs, how are those different?
Right, HNCs, they're kind of the next level up in complexity. Instead of just one type of nanoparticle material, you're deliberately combining two or more different materials, maybe different metal oxides or a metal oxide with a semiconductor, or even a plasmonic metal like gold right next to each other joined at the nanoscale.
Like nanoscale Lego bricks.
That's a great analogy. You're snapping together different functional blocks to get combined properties or maybe even totally new effects that neither material has on its own. The idea is synergy engineering the interfaces between materials.
So building even more sophisticated tiny machines.
In a sense, yes. How they form is governed by thermodynamics and usually involves careful control using organic molecules as stabilizers. There are different strategies to build them. Making core at shell structures is common, where one material coats another. But people also use techniques like cation exchange, where you swap out ions in an existing nanoparticle lattice to change its composition without totally changing the shape. It gives you amazing control.
What are some examples?
Well, magnetic HNCs, like iron oxide cores coated with gold shells, are being looked at for things like separating biological molecules, killing bacteria, improving MRI contrast, and photothermal therapy using light to generate heat. You also see things like yolk-edge shell structures, like an egg, with a core rattling around inside a hollow shell, which can be great for catalysis, protecting the active catalyst core. And even structures where different materials are just joined side by side, like dimers or trimers, where the interface itself leads to unique electronic behavior.
This is getting seriously intricate.
Mm-hmm.
Okay, one last material type you mentioned, aerogels, especially for environmental cleanup.
Aerogels. Yeah, they're really weird and wonderful materials, usually made via sol gel processing, like we discussed for nanoparticles, but then dried in a very special way, often supercritical drying, that removes the liquid without collapsing the delicate solid network.
So you're left with?
You're left with something that's mostly air, incredibly lightweight, but still solid.
Yeah.
You have enormous internal surface areas, super high porosity, very low density.
Mostly air, but solid. That's hard to picture.
It really is. Think solid smoke, almost. And these properties make them amazing insulators. Also great for catalysis support, energy storage like in supercapacitor electrodes or batteries, environmental cleanup like soaking up oil spills or filtering water, even drug delivery and biosensing.
Wow, so versatile. And you can make them from different things.
Oh, yes. Silica aerogels are common, but also carbon aerogels, metal oxide aerogels, even ones based on natural polymers like cellulose or chitsan. You tailor the material to the job.
From insulation to batteries to oil spills.
Yeah.
The range is just mind-boggling.
It really is. And it all stems from controlling matter at this tiny scale, the synthesis, the surface, the structure.
Okay, let's try and pull this all together then. If you had to summarize the key takeaways from this deep dive into colloidal metal oxide nanoparticles, what would they be?
I think the main thing is just their incredible versatility, their adaptability. These tiny particles are really punching above their weight, impacting so many different fields: medicine, energy, environment, electronics, and understanding how to make them precisely, how to control their properties, especially their surfaces. That's the key to unlocking all these applications.
Yeah, that control aspect really came through.
Yeah.
Were there any moments reading through the research that particularly stood out to you as surprising or, an aha moment?
Definitely. I think the direct line you can draw between tweaking a synthesis parameter like laser fluence or reaction time and seeing a measurable difference in, say, how well a drug is delivered or how efficiently a pollutant is removed.
Yeah.
That precision is remarkable. And also the sheer ingenuity in designing those heterostructures, combining materials at the nanoscale to get effects you just wouldn't expect otherwise. That feels like true nanoengineering.
It is a lot to take in, for sure. But hopefully, listening to this, you feel like you've got a decent handle on the core concepts now without getting totally swamped by the jargon.
Yeah, that was the aim, to build that foundational understanding of what's happening in this really dynamic field.
So here's a final thought to leave you with. We've seen how fast nanotechnology is moving. What kind of applications for these colloidal metal oxide nanoparticles might we see in the next 10 years that we haven't even thought of yet? It really feels like the possibilities are wide open. And maybe think about the flip side, too. As these materials become more widespread, what ethical questions should we be asking about their development and use?
That's a crucial point, too.
Absolutely. So if any part of this sparked your interest, maybe the laser synthesis or the medical uses or those weird aerogels, definitely dive deeper. It's a fascinating area, and it's changing all the time.